So again, we're still going to use the end behavior. I see that it's odd, so I know that my end behavior looks like this. Our new strategy is going to be that we're going to find all of our x-intercepts and y-intercepts. And if we have our end behavior and all of our x-intercepts and y-intercepts, we'll get an even more accurate graph than we would with just a table of values. So here's the new strategy. Find all x-intercepts, aka we're going to have to use factoring, surprise, surprise, and y-intercepts, super easy. Y-intercept is make x equals to 0. So the y-intercept is always the very first thing I like to find. Plug in 0 for x, and what do you get? You get 0 for y. Our x-intercepts, we're going to have to factor. And because this one has a common factor of x, we don't even have to use any of the skills we learned early on, right? And you see that it has a common factor of x. And then you already have your quadratic. So our x-intercepts are at x equals 0, x equals -3, and x equals 2. And you can plug in 0 for y to find your x-intercepts. So now when we go to graph, we're going to label our x and y intercepts. So I have 0, 0, -3, 0, and 2, 0. Just going to label. Right? If you don't label anything, you're going to lose an E9 error for graphing. And with these dots and our end behavior, you can draw a pretty accurate graph of what's happening. So I know that the end behavior, it has to start down here. So I go through my point, make a nice smooth curve. This is a pretty accurate graph. The only thing that we won't be very accurate on is exactly how low does it go and exactly how high does it go. That actually is a concept that's left for calculus next year. The best that we could do is we could plug in -2 and plug in -1 and try -1.5 and do a table of values to get an idea. But for grade 12 pre-calculus, they're like, do you have the nice curve shape? Do you have your x-intercepts? Do you have your y-intercept? Is your end behavior right? This is a good enough sketch. So if we find our x-intercepts and our y-intercepts and know the end behavior, we can draw the sketch pretty well. And we're going to go back and we're going to do the question that they did as well, because did you see why this one is kind of cheap? You didn't have to use any of your factor theorem or remainder theorem to figure it out. So the factoring was relatively easy. And then the question in the textbook that we're also going to do this is example 2 here. This is harder to factor. So let's review. First of all, you see that it's even and it's a positive leading coefficient, so we know that our end behavior looks like this. We need to find our x-intercepts and y-intercept. The y-intercept is the easy one. And you see that if you plug in 0 for x, this will be 0 plus 0 plus 0 plus 0 minus 6. Your y-intercept is at 0 minus 6. But to find your x-intercepts, you have to factor. And for factoring, what we learned the other day is that this is your hint. The -6 is your hint. If it factored, your factors have to multiply to give you 6. So your options, because of that 6, your options are going to be ±1, ±2, ±3, or ±4. So your factors could be x + 1 or x - 1, x + 2 or x - 2, x + 3 or x - 3. And you can use either synthetic division or the remainder theorem to find them. Okay? I would start with the remainder theorem only with 1 and -1. So if I plug in 1, can you see that you would get 2 minus 1, which is 1, minus 14, -13, plus 19 is 6, minus 6 is 0. Perfect. X minus 1 is a factor. Go to synthetic division. Everything is in the right order. Nothing is missing. 2 minus 1 minus 14, 19 minus 6. And if you're dividing by x minus 1, there would be a +1 out in front. Bring down your first number. Multiply, add, multiply, add, multiply, add, multiply. Perfect. That's exactly what we wanted. We wanted a remainder of 0. So now you can write your division statement. This is where students often start making some notation mistakes. This question, we didn't have p of x, right? It already said f of x, so you don't have to say let p of x, because it was already labeled. And when we write our division statement, we have to write f of x equals, and we got an x minus 1, and are left with 2x cubed plus x squared minus 13x minus plus 6. And if we have to factor completely, now we have to find a factor in this one. And the hint is still the 6. It's still going to be that you can check ±1, ±2, ±3, or ±6 again. But now you're going to be plugging it into this part. So sometimes I have students do this. We've got f of x already, right? So now I'm going to call this part, I'm going to say let, and you could do p of x now or g of x. Let p of x equal this part. And I could try, and I'm going to cheat a little bit. I'm going to cheat by looking and saying, hey, try 2. Because I looked in the notes and saw that 2 is going to work. Just so we could go a little bit faster. Can you see that if you tried 2, and maybe 2's, right? Remember, as soon as you get bigger than 1, you might not want to use the remainder theorem. You might immediately go to, if I'm trying 2, I would put a 2 out here, 2, 1, -13, and 6. I would go to synthetic division to check, and I want to get a 0 as a remainder. So I bring down the 2, multiply, add, multiply, add, multiply. Oh, yay! It worked. And so this means that x minus 2 is a factor of p of x, and therefore also of f of x. Does that make sense? So now when I write my division statement, I'm going to use f of x again. And I still have x minus 1 from before, but now I figured out that x minus 2 is also a factor, and I'm left with 2x squared plus 5x minus 3. Can you see why this is a good example to do? Because the factoring is way more involved than the one they had off to the side. And this is more likely what you're going to get on your tests and quizzes. because you should know how to factor from the beginning of this unit, and that was the whole purpose, to help us graph these ones. As soon as you get a quadratic, now you can factor in the normal way 2x and x. I'm going to go 3 and 1, plus 3 gives me plus 6, minus 1 would give me plus 5. And if you set that equal to 0, you have 4 x-intercepts. So from before, we already knew that our y-intercept 1, 2, 3, 4, 5, 6 was down here at 0, negative 6. As soon as I label my y-intercept, I've given a scale for my y-axis. Now I'm going to label all of my x-intercepts at 1, at 2, at a half, and at minus 3. So here we've got minus 3 comma 0, 2 comma 0, 1 comma 0, and a half comma 0. And with all of these points, we have enough information to graph it using our end behavior. So remember from the beginning, we had an x to the 4 graph with a leading coefficient that was positive, so our end behavior acted like a parabola that was opening up. So if I start on the left, I know that I have an arrowhead up here. I'm going to have to go down through this point. Now, not a mistake, but a temptation that students do is the following. And we want our curve to be smooth through all of these points. So I'm going to reenact what many students do. Okay? I'm going to start up here. I'm going to go through this point, through this. Whoa! I went too far because, and so sometimes in order to go through this point and then up right away, it's too sharp. So in reality, you don't know how low it's going. I actually, in this one, feel like if I would go lower, it's smoother through those points. You got to kind of feel a flow through each of those points, and that's going to help you. And then we have a pretty accurate graph. What we don't know is we don't know how low this actually went, how high this went. Like, it could have gone up like really high. It's possible. But you want to make sure that you're drawing a smooth curve. You're going to lose a half mark on polynomial graphs if you ever like, ooh, sharp point, ouch, ouch, right? If I can touch your graph and it hurts my finger, I have to take off a half a point. Any sharp points on your graph, because polynomial graphs are always smooth. I'll put, yeah, if it's sharp, I'll put a little bit of red ink on my finger and I'll touch that spot so it looks like smeared blood on your paper for that reason. Okay, I gotta erase the ugly parts. There we go. Nice and smooth. And also, if your graph, like here, went back in time, that's no longer a function, doesn't pass the vertical line test, that's going to be another thing that they're going to look for and say, we have to take off a half mark for the shape of your graph. So polynomial graphs will always be smooth, and if you have the end behavior and all of your x and y intercepts, the graph is going to work out perfectly. Okay. Now, I'm going to give you, to lead into the next idea, I'm not going to give you the equation. I'm going to tell you that this equation was an x cubed graph. A positive x cubed graph. I'll say even though the first number was a 2. Okay? I'm going to tell you that your graph had the following. It only had 2 x-intercepts. It had one here and one here. And the y-intercept happened to be here. And those are your 3 points. Can you draw, with the end behavior being positive, something that would go through all of those points? Okay? But you have to be careful, because when you use the method of finding x-intercepts and y-intercepts, you cannot add any more x-intercepts or y-intercepts. This is the total. So how is it possible that I could start down here and go through all of these points? Okay? First I'll make a mistake. This is wrong. Doesn't it? Everything matches up, but what did I do? I added an extra x-intercept. So that's wrong. How do I do this then?
It bounces.
Goes to here, but bounces off of that, and then goes up. That would work. So we're going to learn next how to recognize when some things bounce, and sometimes they're actually going to, at the x-intercepts, bend.